In this skill, we're going to be using the relationship between change in Gibbs free energy and standard cell potential. In this question, a scientist wants to carry a reaction involving rhenium and copper in an electrochemical cell at 25 degrees C under standard conditions. Here's our chemical equation. We're also given the standard cell potential and the change in Gibbs free energy in kilojoules per mole. Our goal is to figure out the equilibrium constant K for this reaction. Let's head to the reference sheet. Here's our equation that converts between Gibbs free energy and equilibrium constant. Delta G naught is equal to negative RT ln K. The R in this equation is the molar gas constant. Here's the molar gas constant. It's 8.31 joules per mole Kelvin. So we can fill that in here. The T is the temperature, measured in units of Kelvin. We've been given the temperature in degrees C, but we're going to have to convert that into Kelvin. Now remember, the temperature in Kelvin is equal to the temperature in degrees C plus 273. So our temperature is going to be our temperature in degrees C, which is 25, plus 273, which gets us 298 Kelvin. So I can go ahead and fill that in here. K is the equilibrium constant, which is what we're trying to find. Then delta G naught, that is our Gibbs free energy. That's given here as negative 63.7 kilojoules per mole. However, to be used in this equation, we need units of joules per mole. So we're going to have to do a conversion now. We're starting out with negative 63.7 kilojoules per mole. I'm going to set up a dimensional analysis table. And we're going to use the conversion factor. 1 kilojoule is equal to 1,000 joules, because kilo means 1,000. So I'm going to put kilojoules on the bottom, so that will cancel out, joules on the top, and I have 1,000 joules is equal to 1 kilojoule. So I'm going to multiply everything on the top, multiply everything on the bottom, and then divide top by bottom. So the kilojoules will cancel. I'm left with negative 63.7 times 1,000 divided by 1, and my units are joules per mole. So if I put that in my calculator, I get negative 63,700 joules per mole. So I can go ahead and enter that here. Now we need to use this equation to calculate K. I'm going to start by dividing both sides by negative RT, so that will cancel out on the right-hand side. That leaves me with ln K. Now to get rid of the ln, I need to use the inverse function of ln, which is e to the power of. So next I'm going to go e to the power of delta G naught over negative RT, and that's going to be equal to e to the power of ln K. But e to the power of ln cancels out. So we end up with K is equal to e to the power of negative delta G naught over RT. So we can go ahead and put our numbers. E to the power of negative delta G naught, which was negative 63,700, divided by R, which is 8.31, times T, which is 298 in Kelvin. If I put that in my calculator, that gets me out a K value of 1.46 times 10 to the power of 11. So let's go ahead and put that in our answer box here. Remember, times 10 to the power of is written as E on this platform. Awesome. So that's my answer for K, the equilibrium constant. 1.46 E11 times 10 to the power of 11. Awesome. Okay. So now we need to just determine, what does that tell us about the meaning of our reaction? First, we're asked, is the reaction thermodynamically favorable or unfavorable? The way we tell that is by looking at our delta G naught. For a favorable reaction, delta G naught is going to be less than 0. For an unfavorable reaction, delta G naught is going to be greater than 0. In this question, our delta G naught is less than 0, meaning we have a thermodynamically favorable reaction. Then we're asked, is the reaction spontaneous or non-spontaneous? Again, this can be figured out using our Gibbs free energy change. For a spontaneous reaction, that's again when our Gibbs free energy change is less than 0. For a non-spontaneous reaction, that's when our Gibbs free energy change is greater than 0. In this question, we have a Gibbs free energy change less than 0, which means we have a spontaneous reaction. Next, we're asked, will our products or reactants be favored at equilibrium? If our reactants are favored, that means that K is less than 1. If our products are favored, that means that K is greater than 1. In this question, K is times 10 to the power of positive 11. It's a really big number. It's much larger than 1. So in this question, our products are favored at equilibrium. Lastly, we're asked, can this reaction happen in a galvanic cell under standard conditions, or will an electrolytic cell be needed? Now remember, a galvanic cell, that's one where the reaction happens spontaneously and it produces a current. So that happens when our E0 is greater than 0, when it's a positive number. However, if E0 is less than 0, if it's negative, it can't happen in a galvanic cell. It needs to happen in an electrolytic cell because we need to apply a voltage to force the reaction to happen, because it would be one that was not favorable and not spontaneous. In this question, since we have an E0 greater than 0, that's telling us it can happen in a galvanic cell. Awesome. So in this question, we're calculating the equilibrium constant using the changing Gibbs free energy. Remember that R is the molar gas constant. That's going to be 8.31 every time. Remember T, the temperature, has to be in Kelvin. So convert that to Kelvin first before you put it in your equation. And delta G0 has to be in joules per mole. So you're going to need to convert that from kilojoules per mole using the conversion factor 1 kilojoule equals 1,000 joules. Once you've found the equilibrium constant K, you can use all the information provided to figure out what's going to happen in our reaction. If delta G0 is less than 0, K is greater than 1, and E0 is greater than 0, that means we have a favorable spontaneous reaction where our products will be favored and it can happen in a galvanic cell. However, if delta G0 is greater than 0, K is less than 1, and E0 is less than 0, that means we have an unfavorable reaction that is non-spontaneous under standard conditions. The reactants will be favored at equilibrium, and an electrolytic cell will be needed because a voltage will be required to force the reaction to happen.